Hi, everyone. So today, this is probably the third topic talking about the AI. But this time we're talking about like the scale up. So we have the scale up working group established. So today we, like me and Riff will give an introduction to say what do we do in the scale up working group and what we want to do. So this slide I got from the Mihawk. I give credit for the Broadcom team. So basically, to show you, like, say, physically what they look like, because we talking about the scale up, scale out, then what physically look like. So today, as of today, probably the scale up we consider is within the rack. But this is what we're changing. Because the moment, because we have all the COP cables today, because they scale up in the rack, because the COP cables. The moment we solve the COP cable, we introduce the optical cable, we can go even further. Scale out is basically now we even scale out and scale across. Basically, like I say, just mentioned, like the Microsoft, the SRv6 data center, that's huge around that. So that's physically, these are two differences. Then this is from the requirement point of view. So a lot of people were thinking, like, from a scale up point of view, they're thinking that, hey, I extend from the server. So it should be considered a server. That's a wrong perception. I will go detail into there, but I wanted to say, looking at the job scheduling point of view, no matter scale up and scale out, they are the same. So from scale up point of view, from the user point of view, they just thinking each compute tree within the rack is still independent. So they are not considered the whole rack as basically one server. So that's a wrong inception. So that's why I like to say, this time I'm glad that on the first day we have the ESUMs showed up. That boosts a really good momentum to say, hey, now we want to converge from the transport point of view. Because a lot of people are thinking, hey, I can extend the CXL or the PCIe, whatever the bus in there. But in reality, this is not the server. It is a cluster, it's a system. So it's a distributed system. So you need a handling it, all the HA stuff there. Then I'm using the one example. This is come from this year, early this year. The DeepSeek has one paper published. And I'm using one example. They basically compare the scale up and the scale out from the token per second generation point of view. So they basically say, hey, I have the same amount of workload. Then if I go on the scale out, which is the IB network, which is 400 gigabit per second. So they can get the 67 token per second. Then, but if we go a scale up, he's using the NVL72 as one example. Then they say, hey, now I can get close to 1,000. They're very easily to extend it. So then you see that the difference. So from the user perspective, the scale up, one thing is the bandwidth. Because the more bandwidth, you can move in more data, then you could get more token per second those rate. So that's one big advantage. That's why everybody high on that, because your inference eventually will be built on top of those speed. Because you don't want to, like I say, I'm waiting for that forever. So that's the main thing. So then why we come up with this working group? So this is the working group. Today, this is the second time I joined discussing the working group. I joined in the morning talking about the routing working group. This is scale up. Basically, this is like last year, Guohan and I has a talk. I got a requirement to say, build up an Ethernet scale up. He also got a similar requirement. So we say we want to build together because on the SONiC. And then we will get the TF1 from the Broadcom and another GPU vendors. Right now, they don't want to go public to announce it, so I'll let them to announce it. Yeah, but the four of us initially we want to build it. But the question is how we make the meeting. The moment we four of them want to collab together, if we sign, because each of them has an NDA to each other. But if four people come together, you need like the four-way NDA, which is terrible. So that's why we come to the working group. We say, hey, we want to build up this working group and to basically promote the community. That's why we say that's very easy. Under the SONiC working group, at least we can discuss. We don't need to sign an NDA to discuss it. So that's the main purpose. Guohan and I will say, hey, we started the working group. Now we have close to 100 people. And we do the weekly meeting, and we want to generate momentum to see, because I would forecast like this year we only see the chassis, right? Next year in OCP, I bet there will be the real scale-up Ethernet-based chassis will be sitting there. So let's do the bet on that. Okay, so we start with Microsoft and the Alibaba. So on this August 9th, both Guohan and I were in Beijing, China. Then we started to invite Tencent and ByteDance. So 4 of the CSPs join for this one. So you see that this requirement comes from the 4 CSPs coming together. So it's kind of real, yeah. And the other one is like, say, the moment we get the 4 CSPs join, there are other like GPU vendors and I/O die vendors, they all join. So it will be very interesting to see, because initially Guohan and I both are the network guys. We talk in the same language. Now we see the different topic coming in this working group. So then you can see that because this is the whole, because for scale up, the difficulty is like it's a whole system. So there are a lot of things that you need to work with the compute to get in together. So it's not a network only work. So that's why you need to make sure that when you design it, everybody need to agree and participate to work on it. And the other one is like, say, to be honest, from my point of view, scale up will be populated more in China than in the US. Because Trump banned the GPU, right? Which gives the good like opportunity from market point of view. There's no competition. Whatever you build, they're using it. Then you can have time to iterate. Because when I'm talking to Li Hua from Microsoft, they say, I need to compete with NVL 72. Because otherwise, Microsoft compute guy won't using it. I don't have this problem. So that's what the Trump will give the market to the China. Okay, I'm using this one as an example to show you how diversity of this network will be. So the first one is a local China like GPU vendors. Then we have Tencent talking about the semantic layer, transport layers. So in here, so you see that it's already beyond the network guys, right? Then we have Dell talking about the LDP recently. Then we also had Univista. That's a very interesting guy. This is the startup creating the I/O die, the IP, which give it to the vendors. And the funny thing is like they already get the TF1 do the integration in China now. They get it from Tencent. So I talked to the Guohan to say, among 4 of us, Tencent might be the first guy to get the real product. Because they already, so now I give my TH5 because this year I delayed, so I won't be able to get power on the TH5 and the TF1. So I use the TH5. You guys testing with that. So then later on they can compare with the TF1 and TH5. Then following, we just talked about at this moment, we only have 1 rack, right? So we have Zhiping talking about UMP next week, which is talking about like how we extend from 1 rack to the multiple racks. And we also have Tencent, Peter from Tencent talking about what's the Tencent view to changing from the copper to the fiber. So which means that we want to go beyond the 1 rack. Next. Okay, so now I start talking about like from the Alibaba point of view. So this working group start from the initially they say, we talking what do we want? Because we want to build it, right? So we want to talk about, so the first one is like from application point of view, it'll always be a large packet. Guohan and I kind of agree, say, no HPC. We don't want to deal with that beast. Only the AI traffic. So with AI traffic, the life is simple. Then only the large packet will be getting involved. And we probably going with 5, initially 64, because in China they say, even you do 32, it's good enough, because you beat everybody. But we probably start with 64. Then we go gradually move up. Yeah. Then from the chip point of view, we need a high bandwidth, because the DeepSeek already like expanded. Like that means your token per second go high. So you have to have that band. We say the low end-to-end latency. That one, I don't have a good visibility how low will be. So that's why we say just a low latency. Yeah, so that's why I want to wait for the testing result to compare with that. Then the other one, we need a multi-tenancy because natively we are the cloud providers. So we have to have the multi-tenancy support and the enhanced visibility because otherwise the debugging is terrible. Then we want the air cooling, liquid cooling. So that's from my side. Then next. Riff, you want to go with Microsoft? I don't want to hijack Microsoft requirement.
All right, and please pardon me for like maybe 10 seconds. I will fix that notification. I'll come back with it. Yeah, don't want to interrupt what Eddie was talking. Okay. All right. Yeah, thanks a lot, everyone. So basically, from Microsoft point of view, at least from what we see, is that first of all, is the packet size. From application point of view, we don't really see much needs for the the small packets. The packets can be batched, so it's still like fairly large packets, as you can see here. Then the latency is also another interesting thing. We saw like in the scale-up network, lower latency is almost an absolute must, but it turns out to be not really. Right now it's at less than one microsecond, and preferably like 600 nanosecond is probably already good enough. So the traffic rate is another thing. We need huge amount of traffic, like bandwidth. So ideally is that the total bandwidth of the GPU is can match with HBM bandwidth, which is actually quite stressed. Also another thing is multi-tenant. So we do have use cases for multi-tenant, which is actually at the GPU or node level. I don't see anything come up yet that goes within the GPU that splits the GPU into multiple partitions. Hardware-wise, we don't have like liquid cooling or copper. One small thing is that we do have are seeing the requirement for the N-1 service interoperability. The reason is that you may have like multiple different hardwares being developed in parallel. The switches and the GPUs are developed in parallel. So you could end up with an early stage of verification where you use old generation and connect with the latest generation on the other side. So N-1 definitely will help with that. Network protocol-wise, L2, everyone is doing that, but we do see like people because think from the the packet size point of view and latency point of view, maybe L3 is also an option, so we don't want to rule out that from the table. And with L3, of course, PFC, ECN, all these things will just be there. Even in the L2, PFC is also doable as well. So operational-wise, monitoring is definitely something key that we need to think about. One thing for the monitoring is that the high-readiness ports definitely will add, a lot of overhead on the counter pooling. So we do see like high CPU usage on many different components in the system. So this may cause a problem and needs to be fine-tuned. High-frequency telemetry, we just already talked about. Yes, then it will definitely help debugging, the AI traffic. All right, so that's everything. Yeah, thanks. I'll go get it back to Eddie.
Go next. Yeah. So after like Guohan and I invited Tencent and ByteDance to join, so we also get the Tencent's requirement and ByteDance requirement. So this is the Tencent's requirement. So you see that they start with more like say 32, actually very real. And their 64 GPU part is like a 2-node, 2-rack back-to-back. So it's very unique. So it's good like we see the different view on that. Then also they want to go eventually go to 512, which they call the Ethernet Ultra, which is also the optical approach. Then they want like the 1 microsecond. I forgot they are the round trip 1 micro, or this is like say one-way 1 micro, but we have recording on that. Then packet size also like I say this is a 4K packet size. So they introducing the two things. One is the memory semantic, or which kind of like RDMA-like this approach, which you do the copy the data. The other one is a 512 byte, which they call memory semantic, which is a load and store, which is semantically like you go with the AXI bus to get the instructions and do packaging there. From forwarding point of view, they also say want to like say IP routing, and also they will prefer to using the compression headers. And congestion is kind of similar, so I won't go. The interesting part for the working as a server, so that's from operational point of view, because you think about this, although we say, hey, you're using it individually, but from the configuration point of view, you want to be as static as possible. So they was working as a server, so it means that you don't want to touching it as much as possible, right? So leave it as long. So that's one, yeah. Then we come with the next. Then we come with the ByteDance. So the ByteDance start with the 128. Actually, they also talking about 32 and 64. It's very interesting. They both company talking about the same thing. So I asked them individually. I would say, well, you guys talking to each other? Because they also have the 32 with one rack and 64 by 2 rack by back-to-back connected, but they say they come up individually. They didn't talk to each other, so it's very funny. But they want to like go into the 128 or 1K eventually. So packet size also the big, and latency-wise, one of them claims one way, one of them claims two-way. I forgot which one. They're also asking for the multi-tenancy because of the cloud requirement. From then the other one kind of similar. So now we see that we have 4 of them, so we put them together. So then this is the table which is already in the architecture document. This is the open, you don't need to take the picture. This is in our architecture document. So you see that once you put all 4 of them, you put it then looking horizontally, you see that there's a commonality in between. So that's the main purpose. We want to draw the table. So now everybody will be clear, say, what's the commonality in between, right? So you see that from packet size point of view, kind of similar, the big packet, right? 1K at least minimum. Then the cluster size, everybody start from small and going to up to 1K. Probably Google guys go even further to the 8K or 9K for the OCS, but I think here on the Ethernet, everybody a little bit hesitate to go that high. But at least we will go with one rack, then multiple rack to going further on the top of it. Latency-wise, I think everybody just say low. How low would be? It's need to test it, right? So then from the traffic rate to kind of similar, basically say we need to meet the memory bandwidth. That's the basic stuff. Then multi-tenancy is kind of same, so everybody the same. Forwarding, you see layer 2, layer 3, like Microsoft want to layer 3, I'm fine with that also. So eventually, it's just a forwarding, right? Then from an operational point of view, I think the monitoring is a key. So everybody talking about the monitoring. And so it kind of like, because you don't want to get another beast, it's hard to manage in your network. So simple, reliable, that probably will be the key. Okay, then next I will probably give to the Riff to talk about our architecture part.
Yeah, all right. Thanks a lot, Eddie. Okay, so basically with all the requirements and coming from the community, we come up with this Ethernet scale-up AI cluster architecture. I think right now, the screenshot is a little bit old. Right now it's a version 0.6, should be, and it's actually published already in the GitHub. So if anyone is interested in, feel free to check it out. Give us comments, feedbacks, then it will be really appreciated. Okay, so when people are talking about like AI network, I think one name will definitely pop up is the UEC. So what's the difference between those two groups and what's the focus? So I think on the UEC side, huge congrats on the 1.0 like release. UEC will currently mostly focusing on the scale out side of the network, while we are mostly focusing on the scale up side of the network as the purple side and the the red. Shows highlights over there. Okay, okay. So the characteristics is slightly different or very different. So that's why we're actually focusing on different things. Okay. So I think in the beginning of the architecture talk is actually the reference system model, how things gets modeled. So basically on the very top level, all the GPUs will be interconnected to each other within a single domain. And then inside of each GPU, you can see each GPU will have like all this multiple stations inside, and each station will actually have a unique address can be actually identify every single station. So each station can be further broken down into multiple ports that can be connected through multiple links, through multiple uplinks to different switches. And all the network you can see is commonly currently in a single tier, single hop network that limits the latencies and other things. And I think some people may think about like expanding the scale-up network into the multiple layers or multiple hops, but right now we'll start with a single hop, single tier network at this moment. Okay, so one key thing is that what drives the design is actually the bandwidth. The bandwidth is that a lot of the requirements is to actually match the GPU memory bandwidth that goes to how much the HBM can do. So the current is that the previous version is actually the HBM3E, and now everyone's moving towards HBM4. And we can actually do a really quick calculations. In order to actually support this bandwidth, each GPU will need a huge amount of ports being created, and that creates a lot of like challenges in the system design, which we'll talk about slightly later. All right, and then the entire system can be connected using copper, and we're expanding to the optics as well. It's really like this gives us a flexibility going beyond one single rack. Okay, and another thing we just talked about the multiple uplinks. So different people use different multiple uplinks maybe for different reasons. So some people may think that they use it for load balancing. Some use cases may think that they actually use for like reliability. But keep one thing in mind with multiple uplinks is that the memory is very bandwidth hungry. Okay, so when you have multiple bandwidths, you better use them fairly wisely. Okay, and then it goes to the last item is that we do support various ways, or we do see various ways for the failure handling. Different company or different it's actually doing different things. Yeah, there's no single silver bullet for the failure handling purpose. All right. Okay. And we just talked about how many ports we need to fill in the HBM. Okay, and how many ports do we have in one single ASIC? So we already talked about like the right now it's 512 radius. So at maximum one single ASIC right now is 512 ports, and with this like one single GPU that needs like 21 or even more ports. So how do we solve that? So very gladly, SONiC already has a multi-ASIC architecture. So and this commonly used currently in the T2 chassis. We can actually doing the similar things to actually solve this problem. So you might also wondering like, can I just shovel like more switches into the rack? So that's probably okay, but the more switches you put in, the less rack space you can actually put there for GPUs. So rack space is limited, so that may not be also a nice choice. And there we go, multi-ASIC. So with that, every single ASIC will have its own protocol stack and control stack. For example, SWSS, SyncD, SI, and with all the LLDP, all these protocol stacks as well. So with that, different ASIC can be programmed like differently, then enable us to actually put more ASICs within a single switch that saves the rack space. So this is something like we probably need in a scale-up network. All right, and now let's talk about a little bit more on the proto stack. Okay, so this topic maybe is slightly large, but we'll start from the transaction. Everything starts from transaction. So it's all the RDMA read and writes and everything. Then from that, we go to the transport, which packs all the requests into the packets that can be sent out, or the requests can be sent out. And then from there, we go to the adaptation layer, which actually provides, for example, that's where the plan lookup and everything actually start to happen. So it determines that the packets already in the buffer that can be which lambs or which paths it should be sending out and that's adaptation layer, and this is very likely the very first layer will probably have something in it, and because the adaptation layer works with the network layer to see which link is actually alive or good, and that involves, like, for example, link probing, for example, PFD, and these things will happens in that layer. All right, so going to the next one, once it knows which plane it goes out, it goes to the network layer. So network layer does auto forwarding. It determines then which GPU it actually needs to go to. It packs the packet and everything. And in here, you can see we have the not just the regular L2 forwarding. We also have the optimized header. We'll talk about very soon. It's a different or dedicated protocol that can be leveraged in the AI scale-up network. So once a packet gets created, it will go through the the Ethernet layers and link layers. Eventually, the packet goes out. On the Ethernet MAC layer, we can see the LDP will actually being used over there. So the entire network is somewhat static. So you might not really need LDP for neighbor discovery, but here the LDP will actually be there in order to actually help the, for example, link level retries and CBFC to actually get established. So on the link layer, we also do support like PFC, and once a packet goes out and actually does hits a file layer, we do expect auto negotiation, link training, and also FAC being enabled. That just gives you like better link reliabilities. Otherwise you hit bit errors, and that's just not fun. All right, so that's a whole protocol stack, and we just talk about the some headers. And optimized headers or compressed headers. So on the top is actually the very standard, the L2 layer headers, as you can see over there. However, in we do see some of the requirements that actually needs small packets. For example, in the Tencent, they have like CPU to remote GPU memory access. Those packets can be as small as 128 bytes. So with that, the size of the MAC header is actually becoming fairly noticeable if you actually transfer a lot of like small packets. So in this case, we can actually use a compressed header, which reduces the packet size from 18 bytes, as it shows up out there, to 14 bytes, with everything like being placed inside. So the destination and the source, like those Bs, there are like 2 bytes for them. It's already enough to cover all the use cases right now. So this is very very helpful. It's going to be very helpful. Okay, so that's forgot to mention that. The packet format of the header is called AI Fabric header. It's actually being defined in the SUE. So if you are interested in that, feel free to check it out. There is a huge spec, talking about all the details over there, including all the pipelines and everything. All right. Yes, thanks. Okay, so. The next one is actually the configurations. We mentioned that the network is pretty much, majority static. So, but still needs a control plan to program it. So in this case, we can actually have a, the SDN controller programs everything like into the switch and make sure everything works. So we do need several protocols being enabled, but it's fairly minimum. For example, like LDP or BFD or other type of like link probing. But this is pretty much the protocols that we need. Okay. So now where are we? All right. So the whole working group, like all the effort starting from the January, and then it actually gets kicked off from at March. We are currently at the architecture version 0.7, which is slightly behind the schedule. However, that means that we are still working towards that. And if everyone or anyone is actually interested in that, feel free to join us. And after that, we'll once the architecture doc is finalized, we'll go into the model designs and all the side API definitions, other things. So this is the whole like the at a high level, where are we? Okay. Okay. So. Yeah. So last one, call for action. So if you're interested in the whole, whole effort, feel free to join the Scale Up working group and the weekly discussion. We have a weekly discussion meeting. The link is actually in the working group homepage. It's quite a long link, so I'm not going to paste it here. But another thing is that the architecture doc is actually out for review. So share your feedback. Let us know how things go, what you think. It will be really appreciated. All right. So that's everything. Yeah. Thanks, everyone.
Thank you, Eddie. And thank you. Any questions for the speakers?
Yeah, so I wanted to, Mike Capuano, I wanted to understand how you mentioned eSON. How does eSON fit in there? Is that where you guys are headed? We're using that at the lower layers?
Yeah, that's a good question. First of all, I like the eSON name better than the SUE. SUE, I feel like we are going to lawsuit very soon. So eSON basically say like you can think about like he mentioned like the Ethernet headers, right? So anything below is Ethernet, right? So that's what we're doing right now, and above it it's end-to-end, which you could do like UL, you could do the UEC or the SUE, whatever it is, right? So this is end-to-end because from my point of view, like say, end-to-end is more like driven by the GPU vendors. It's very hard to convince everybody agree on the same thing because there's no interoperability really required. But for me, at least, I need to make sure that everybody going with the Ethernet, we're talking about the same thing. See, just like Riff mentioned, like we have the CPFC, we have like a PFC using the control, do the like flow control. Then you using the LR, those things. Those are basic stuff is there. So that's the main thing. So from my point of view, eSON is basically say, it's aligned together. We are only the software part, but eSON will also have the hardware part. That's the main difference, yeah.
Yeah, so thank you for the working group archive. Actually, I watched all of them, and it helped understanding the requirements. It took like 3 days, by the way. And one question about configuration model. For at least for initially, I believe that all the switches would not be connected together, at least at data path. And you mentioned about the multi-switch ASIC feature and also the SDN kind of API. So do you expect for the one-layer initial setup to also use this multi-ASIC feature, or it's only for 2 or more layer features?
Sorry, I might need help to repeat the last part of the question.
Yeah. So do you expect that even for the initial single layer, you could use multi-ASIC feature, which
right.
Or
Yeah. Even with a single layer, like in the very beginning, like single hop, single tier network, the multi-ASIC will actually be very helpful as well. Because if you think about the NVL, let's say NVL 72, right? So that rack has 72 GPUs interconnected with each other. So each GPU will actually have a lot of ports. So if you do some calculations, a single ASIC is not going to actually support that. So that's where like you also don't want to really shovel in like more switches because then you reduce the number of GPUs you can actually put in the rack, and then it creates a problem with you have to connect the multiple racks, then copper would not work. So then that's the case that the single switch with multiple ASICs inside will definitely help to fix that problem. Yeah.
So do you expect which would be used more, or?
I would expect the multi-ASIC will be used more. not just a single ASIC. Yes, yes, because the space is limited. And yeah,
Okay, thank you.
no problem.
All right, if no more questions, we'll take one last break before the last set of sessions. Let's all come back at 2:10.